Hi everyone, so in this video we'll be discussing quiz chapter 8 set 1. So here let's look at the first question that many of you got it wrong. Question 2. What forces do not cause any torque? So they give you 4 different kind of forces, then they ask you which one will not cause any torque. So let's bring back this diagram. So this is a diagram being enlarged over here. So we know that this is a plank being supported on a fulcrum. So we should expect this place to be our pivot. So this place will be lock. We should expect this place to be our axis of rotation. So now let's look at all the 4 forces that are being stated here and see which forces here will contribute 0 torque if we take this point over here as our axis of rotation. So the first force is the force perpendicular to the plank exerted right at the fulcrum. So a force that is perpendicular to a plank can be either upwards or downwards. But if you exert it right at the fulcrum, that means you're either exerting it in this direction or this direction. Well, if you're exerting the force right at the fulcrum, then you should expect this force to contribute 0 torque. Why does it contribute 0 torque? Because torque, the formula is Rf sine theta. So the biggest issue here why your torque will be 0 is because your R here is 0. So your R is 0, therefore your torque will be 0. So therefore you should expect 0 torque for the force perpendicular at the plank exerted right at the fulcrum. So let's look at the other questions as well, the other options as well. So you have a force which is slightly off center of the fulcrum. So that means you exert a force, but that force is slightly off center. So probably somewhere here, maybe. It didn't state that whether the force is perpendicular or at an angle. So in this case, we just assume that it's something like this. So if the force is exerted somewhere away from the fulcrum, then you have your R. You get your R, which is measured from here to here. So if you have R, if you have F, then this R and F has components which are perpendicular to each other, then you expect this one to have non-zero torque. Okay, so this one will have torque. Next, force perpendicular to the plank but exerted at the far end of the plank. So if I clear things up over here, force exerted at the far end of the plank will be exerted at somewhere over here. So this is the far end of the plank. This can also be called the far end of the plank. So if you exert a force somewhere here, perpendicular to the plank as well, then you should expect here to create a large torque. Why you should expect a large torque over here? Because the distance, the perpendicular distance away from the axis of rotation is large. So if this one is big, then of course your torque over here will be because you have a large R, therefore you should expect a large torque being produced. Okay, if you assume all the force have the same magnitude, I mean for all 4 options here the force have the same magnitude, then this one exerted at the far end of the plank will probably have a greater torque than this torque produced by the force that is off center of the fulcrum. Okay, last one, we have a force at a 45-degree angle to the fulcrum and not on the fulcrum. So the force is not exerted on the fulcrum, so you can think of it as either slightly off center or far off the center of the fulcrum. Then with that case, you have an R. Your R is no longer 0. So if I take an example, it could be something like this. So your force is something like this. Then it has a degree angle of 45 degree. So if your R is measured from here to here, then your torque will be Rf sine 45 degree. This is the magnitude of the torque produced by this force over here. So of course you should expect R to be not 0, F to be not 0, sine 45 to be not 0. Therefore you have a non-zero torque being produced. Therefore, you should expect the fourth option here will also produce a torque as well. So all three options over here produce a torque. The only force that does not produce a torque is the force that is exerted right at the fulcrum. Because if you exert the force right at the fulcrum, the distance away from the axis of rotation will be 0. Therefore, the torque produced will be 0. So that will be our answer. So let's look at the next question. Which diagram, question 3, which diagram shows coplanar forces, means like forces that are exerted on the same plane. It's like everything is 2D happening on the same plane. Okay, so each of the force has magnitude of F acting on the disc. Now they ask which diagram here, the force acting on it is in equilibrium. So if a force acting on the disc is in equilibrium, what you should expect is, you should expect this in equilibrium means that the sum of force should be equal to 0. At the same time, the sum of torque should be equal to 0. So sum of force equal to 0 will cause the object to be at rest or moving at constant velocity. Okay. Whereas if your sum of torque is equal to 0, it can be the object not rotating, or the object is rotating at constant angular velocity. Angular velocity is omega. Okay, so this is what we need to check. So let's look at sum of force equals 0 first. Let's see which diagram here obeys this criteria where the sum of force is equal to 0. Well, we have to beware that each of the force here have the same magnitude. That's why they label everything by F. If they have different magnitude, they'll probably label it as F1, F2, or F3, or F2F, something like that. But since everything is labeled with the same symbol F, you should expect each of the individual forces here to have the same magnitude. So now let's look at the first criteria, which is sum of force equals to 0. You should expect any force pointing up to be balanced by a force pointing down. Any force pointing to the right should be balanced by a force pointing to the left. So if you look at the first diagram here, there is a force pointing up and it is balanced by the force that is pointing down. So you take up plus down. So positive plus negative both have the same magnitude. Your answer will be 0. So this one fulfills sum of force equals to 0. Let's look at the next situation. You have force being applied at an angle. Okay, so if you look over here, you have some amount of force that is pointing upward and rightward. So it has to be balanced by something that is pointing leftward and downward. So you have something that is pointing leftward, that's good, and you have something pointing downward, that's good. So that means it's possible for this force to be cancelled out. Next, you look at this force over here. This force over here has have a component pointing upwards, have a component pointing leftward. So you should expect there's a force pointing rightward and downward in order to cancel it out. So this force here has a component rightward, so you can balance out the left component over here, whereas the up component here can be balanced by the down component over here. Okay, now we have discussed this force, we have discussed this force, we move on to the third force. This third force over here has most of the force is dedicated downwards, so it has a big Y component, but here you have two forces which has an up Y component. So it's possible that these two forces, their vertical component, can cancel out the vertical component of this vertical downward force over here. So it's possible for this setup here to have sum of force equals to 0, because there's a right component to cancel out the left component, there's an up component to cancel out the down component. So this one we can say the sum of force can be equals to 0. Next, you look at the third diagram. Third diagram, you look at the force one by one, starting from a force at the left. This force here has a component which is pointing to the left and pointing downward. So the component pointing to the left can be balanced by the third force over here, which is a component pointing to the right. They can balance each other out. But there's a component of force in this first force here that is pointing downwards. So the downward component here should be balanced by a force that is pointing upward. But you look at this whole setup here, there is no force pointing upwards. So that means by the downward components of these forces over here will not be balanced by any forces pointing upward. So in that case, this force here will definitely be unbalanced. So we can say that this one, the sum of force, is definitely not equals to 0. So you can eliminate this diagram from your discussion now. Okay, next you look at the fourth diagram. The fourth diagram has 4 forces, more forces than earlier. So let's check each of the forces, whether they have forces, they have components in the opposite direction to cancel them off or not. The first force has upward components and leftward components. You know that it needs to be balanced by a downward and a rightward component. The downward component can be obtained here or here, and the rightward component can be obtained here and here. So it can be balanced off. Next, this force over here has a leftward and downward component. Leftward need to be balanced by rightward. So these two forces here can act to balance it out. The downward component here need to be balanced by something in the upward component. So upward component can be found in these two forces over here. Next, the third force over here has a upward and rightward component. So it need to be balanced by downward and leftward. Downward can be found in these two forces, leftward can be found in these two forces, so it can be balanced. So I believe you know for the fourth force over here, it can be balanced as well. You need a left component and a upwards component. The left component can be found here, the upwards component can be found here. A simple way of thinking about it is this force here will be balanced by this force, whereas this force here will be balanced by this force. Therefore, the sum of force should be equals to 0. Okay, so from this discussion, we have successfully eliminated one of the setup. So now let's move on to the second criteria, which is sum of torque need to be equals to 0. So if you look at this situation here, our axis of rotation will be at the middle. So this force here will definitely create a torque because there is R and there is F. Both R and F are not 0 and the angle is 90 degrees. So RF sine 90 degrees definitely equals to RF. So therefore you should expect there's a torque produced by this force over here, and the torque will cause the this to turn in an anti-clockwise direction because the force is pushing upwards, so it will cause this to rotate anti-clockwise. So anti-clockwise, I will label it like this. Next, you look at the second force over here, this downward force over here. This downward force over here again has a distance r from the axis of rotation. So you should expect r to be the same as the r for the first force over here because this is coming out from the center of the circle. So they both have the same r, they both have the same f, but this rf here will produce a torque, but in what direction? Well, your force is pointing downwards, so it will cause the disc to rotate in a anti-clockwise manner as well. So this is an anti-clockwise torque as well. So if it's an anti-clockwise torque together with an anti-clockwise torque, they will not cancel each other out. Both of the torque produced by these two forces here are anti-clockwise torque. So they will add up to each other, causing a greater angular acceleration. Therefore, for this situation over here, the sum of torque is definitely not equal to 0. These two torque doesn't cancel each other out. You need one clockwise and one anti-clockwise of the same magnitude, only the torque can cancel each other out. But this is not the case. So we can say the sum of torque is not equals to 0. Okay, next we look at these three forces in the second setup over here. This force over here, okay, I might need to draw the center. Oops, this is definitely not, does not look like the center. Center is somewhere here. So your R will be pointing like this. Okay, so it's definitely not not 90 degree, but it's not 180 degree either. So there will be a value. There will be a torque, just that the torque is smaller. This one will have an R as well. Okay, it's optional whether I want to label the vector sign or not. So this one will have an R as well. Okay, so all of them will probably have the same angle. Okay, we are not sure of the angle, but we should expect that all three of them will have the same angle over here. Okay, so let's label theta, theta, theta. So you should expect the torque produced by all three forces here to have the same magnitude because they have the same R, they have the same F, they have the same theta. So if you calculate RF sine theta, you should get the same magnitude for the torque produced by all three forces over here. But whether they cancel out or not is the main issue that you want to look at. So if you look at the first force over here, this force over here will cause the rotation. This force is exerted in this direction. So if you pull in this direction, you pull the disc to rotate in a clockwise fashion. So this is a clockwise torque over here. Next, if you look at this second force over here, this second force, if you take your center as the axis of rotation and you pull down here, it will cause the disc to rotate clockwise as well. So you should expect this to be a clockwise torque. Lastly, for the third force over here, this is your axis rotation. You are pulling your disc, something like this. You are pulling it up like this. So if it's pulling up like this, then you should expect the rotation to be a clockwise rotation as well. So therefore, this is also a clockwise torque. So all three torque produced by these three forces here are all clockwise torque. So it is not possible for them to cancel each other out because there's nothing in the opposite direction. All these torque are in the same direction, they will not cancel each other out. So the torque is definitely unbalanced, therefore the sum of torque is not equals to 0. Okay, so we will skip the third diagram over here and focus on the fourth diagram over here. The fourth diagram here, you have four forces. Let's analyze this force over here. Again, we'll start by putting down the axis of rotation. Then we will label the R. This is the R. This is the R. This is the R. This is the R. Okay, I believe you noticed that the angle between the R and F should be 180 degree. And if you are doing RF sine 180 degree, sine 180 degree here will be equals to 0. Therefore, the torque produced by all these forces here will be 0. So the torque produced here will be 0. 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 Therefore, all the torque here, all the forces here does not produce any torque. Therefore, the sum of torque will be equals to 0. Okay. So with that said, we know that this is the only setup that has sum of force equals to 0 and sum of torque equals to 0. And this fulfills the criteria of this being in equilibrium. That's why our answer will be the fourth diagram over here. Okay, so that's how you solve question 3. Next question. Question 3. A light rod PQ pivoted to the wall at point Q. So you have a light rod, which is a massless rod. If you see light rod in physics, it means massless. Okay, so it's pivoted to the wall at point Q. So here you should expect there's a pivot or a hinge. And it's as shown in the figure above, a diagram above. So the rod is held in a horizontal position. So this is horizontal, by a string which is attached to point R that is vertically above Q. So point R is vertically above Q, and this point R here is connected to a string which is connected to the point P, the other end of the light rod PQ. So this rod here is able to maintain in horizontal position because this string over here is hanging it, connecting it to point R that is vertically above point Q. A load is hung at the middle of the rod. So you have a load over here and it is hung at the middle of the rod PQ. So if the load is moved towards P, so now if you shift the load towards the left, which quantities will be decreased. Okay, so how we are going to solve this problem? Again, we start by drawing the free body diagram to illustrate all the forces that are acting on the light rod PQ. So this is the diagram being enlarged, and I'm going to draw the free body diagram for light rod PQ. So we should start by having a line to represent the light rod PQ, a horizontal line. Then we will start by asking ourselves the 5 questions. The first question is whether the light rod PQ here has weight or not. Well, if he says light rod PQ, I believe we can assume it to be massless. Therefore, we assume this rod here to have 0 weight. Next, the next question is the light rod PQ here connected to any strings, ropes, or cable? Yes, it is connected to a string at point P, and in the middle, it is connected to another string which connects to the loop. So you should expect 2 tension in your diagram. So let's call this tension 1, and we have tension 2 coming out from the middle. Okay, the third question to ask ourselves is whether there's any force being explicitly stated in the question or in the diagram. Well, in the diagram, they didn't mention any kind of external force. In the question, they didn't mention there's any kind of external force being exerted on the system. So in that case, there will be no external force. We move on to the fourth question. So in chapter 8, we usually ask about friction first. Is there any position where the friction is relevant or not? Is there any rough surface? Well, the only point where the light rod PQ is touching something, it's point Q. So point Q here, there's a possibility for it to have friction. But if you look at the statement here, they mention that it is pivoted to the wall. So maybe it's some kind of a hinge structure or a pivot structure over here. So if it's a pivot structure or a hinge structure, what we do is we'll try to not look at the friction. We'll let reaction force we'll try to determine the reaction force instead. Because the reaction force is a combination of normal force, the force that is perpendicular to the surface, and the frictional force, the force that is parallel to the surface. Reaction force is a combination of both. So if we choose to determine reaction force, then we don't need to determine the frictional force or normal force at that point. Okay, so since we are doing so, we are treating it as a hinge. We are not looking at its normal force or frictional force. Therefore, we will straight away skip friction for this point and look at the reaction force instead. Okay, so we look at the reaction force at point Q. To determine the direction of the reaction force at point Q, what we need to do is imagine we make this wall disappear. Technically, we make this pivot disappear. But to make it clearer, let's make this whole wall disappear. But point R still remain there. This portion of the wall still remain there, but the whole portion of the wall here disappear. Technically, I want to make this pivot disappear. Okay, so when I make this pivot disappear, what will happen is the string is my finger over here, then this pen here represent light rod PQ. When the pivot here disappear, what will happen is you should expect the point Q to be falling, right? Because there's nothing holding it in horizontal position, so it will be falling like this. At the same time, if you are not held to the wall, what will happen is the string should be swinging towards something like this, right? The string should be swinging like this. So you should expect this end of the light rod PQ here, this point Q over here, to be falling while at the same time moving to the right. It should be falling while at the same time moving to the right. Something like this. Okay, falling while moving to the right. Therefore, if you have a reaction force to prevent it from falling and moving to the right, then the reaction force should be opposite to this falling and moving to the right, right? You want to prevent it from falling and moving to the right, so you must exert the force in the opposite direction, which is upward and to the left. Therefore, your reaction force should be upward and pointing to the left. Upward and pointing to the left, if you combine it back, this is what you get, R. Okay, but if I want to do it as R, it's okay. If I want to do it as Rx and Ry, that's okay as well. But let me label it as R. Okay, So that's it. Okay, if I want to label, let's label this as theta 1. Let's label this as theta 2. So we have asked ourselves the 5 questions. Thankfully, we are done with the free body diagram. They didn't give us any length measurement, so it's okay to leave this free body diagram here without any length measurement. Okay, next, when we finish draw our free body diagram, technically what we should do is we should look at which value do we have, which value do we not have. Let's try to change this tension 2 into something else. We know this tension 2 here is connected to the load. So if you draw the free body diagram of the load, we should expect that there's the weight of the load and there's tension pulling it upwards. And since the tension over here, it belongs to the same rope that connects to light rod PQ, you should expect them to have the same tension. This tension at this portion of this tension exerted on light rod PQ at this point should be equal to the tension exerted on the load at this point. So therefore, you can call it by tension 2 as well. So now once you have do that, you know that this whole system is in equilibrium. This load here is not moving, it is at rest. Therefore, you know that the sum of force in the y direction should be equals to 0. So therefore, you know that tension 2 minus the weight of the load should be equals to 0. Therefore, tension 2 is equals to the weight of the load. So now you can replace this tension 2 in the extended free body diagram with the weight of the load. Okay, so this is the revised extended free body diagram. Now we can start to do our work. Technically, what we should do is we should determine which value here do we have, then we put ticks and crosses, then we decide where is the axis of rotation, right? But for this situation here, we have no value given at all, so we can skip that step. Technically, we don't have any values given. All of these will be crosses. Okay, so now we should move on to choose our axis of rotation. Okay, so if you look at the question here, right, it says if the load is moved towards P, which quantities will be decreased? That means we are interested with the quantity of the reaction force at Q. We are interested with the quantity of the vertical component of the reaction at Q. We are also interested with the tension, and we are interested with the horizontal compressive force in the rod. Horizontal compressive force in the rod, right, is this tension here resolved to its horizontal component. If we resolve to the horizontal component, then this horizontal component here is technically compressing the rod, right? This force here is compressing the rod. And it should have the same magnitude with the horizontal component of the reaction force. If you resolve the tension and you resolve the reaction force, you should see that these two forces have the same magnitude because they need to be in balance. So one will push to the right, one will push to the left. We call it a horizontal compressive force in the rod. Okay, so they say this horizontal compressive rod, which is these two being resolved to its horizontal component. So that means you are interested with the tension, you are interested uh, with the reaction force over here. If you're interested with both of these things over here, that means we should not put our axis of rotation on any of these two ends over here. Because if you put your axis of rotation on a certain point, you lose all information you want to know about that force exerted at that point. We always pick a point to be an axis rotation because we are not interested with that something over there. But now if you look at the option of the answer here, you're interested with tension, you're interested with the reaction force, you're interested with both, so you should not put your axis of rotation on any of these 2 points over here. Okay, so that means you should pick any point that is not belonging to the 2 ends of the point. So let's pick a random point. Let's pick this point as our axis of rotation. Okay, it's a random point, but I believe it will be able to solve a problem. Okay, so let's pick this point as our axis of rotation. If we pick this point as our axis of rotation, let's try to construct our equation. Okay, let's make a table then. Table of 5 columns. So you have your fx, you have your fy, you have your plus minus r and your f perpendicular. Okay, so for tension 1, the fx here will be tension 1 cos theta 1. The fy will be tension 1 sine theta 1. Plus minus, whether it's a positive torque or a negative torque, we need to see whether this torque here is a clockwise torque or anti-clockwise torque. So hold our pen here to represent the light rod, pin ourselves at the axis of rotation, then try to push the same way as the tension looks like. So the tension is in this direction. So if we push in this direction, we see that the pen will rotate clockwise. The pen rotate clockwise means it's a negative torque. So the r here, we have to define r. Let's call this distance here as r1. Okay, it's always measured from the axis of rotation to the point where the force is being exerted. Then the force perpendicular will be T1 sine theta 1. Okay, technically you are breaking this up, finding the component that is perpendicular. Okay, next we look at the weight of the load. The weight of the load, there's no x component, there's only y component. The y component is the whole weight of the load, but with a minus, because this weight of the load here is pointing downwards. Okay, now if you look at the plus minus, the plus minus here, you have to determine whether this weight of the load here produce a positive torque or a negative torque. So hold your pen at the axis of rotation, which is slightly to the right, then push at the center downwards. When you push at the center downwards, you see that this rod here will rotate in an anti-clockwise fashion. So therefore, it's a positive torque. Then the r, the distance from the axis rotation to the point where the force is being exerted, this one we call it r2 then. So this is r2. Then the f perpendicular is just the whole weight of the load. Okay. So next, you look at the reaction force. The reaction force, the x component will be negative r cos theta 2. The fy will be r sine theta 2. Okay, we resolve this. The x component is pointing to the left, therefore we put a negative sign. The y component is pointing upwards, therefore we still remain at positive sign. Okay, so let's see whether this reaction force will produce a positive torque or a negative torque. So pin ourselves at the axis of rotation, try to push like the reaction force. If you push like the reaction force, you see that it will cause the pen to rotate anti-clockwise. So this is a positive torque. Okay, so now we label the distance here as R3. So the perpendicular component should be r sine theta 2. Okay, so once we know that already, we know that this portion here will be the torque, because torque is equals to r f perpendicular. Okay, if you assign component z, then you can put in the plus minus in front. Okay, plus minus, the z here is showing that it's a z component, so if it's anti-clockwise, then it's a positive z direction. If it's clockwise, then it's a negative z direction. That's where you put in. Okay, if you keep your equation as just tau, then that means this is magnitude, then magnitude must always be positive, then therefore it will be r f perpendicular. F perpendicular is just f sine theta. That's why if you expand it back, you get r f sine theta. Okay, so let me change my So I'll cover until this part. Okay, then later I'll say plus torque of what minus torque of what. Okay, so the sum of torque is equals to 0. So the sum of torque is equal to 0, then it consists of a negative torque due to the tension plus a positive torque due to the weight of the load plus a positive torque due to the reaction force equals to 0. So you can shift the torque due to the tension to the other side. You can do that as well. So this will be torque. This left hand side of the equation here will be torque in torque anti-clockwise, whereas this right hand side of the equation will be torque clockwise. So torque anti-clockwise should be equals to torque clockwise. Only they are balanced, then the object won't rotate, or it will rotate at constant angular velocity. So now once we know that already, we can try to do our substitution. Okay, so now we are substituting in torque. We already put in the sign already, so don't worry too much. So we just substitute the torque only, so it will be R1, R2, weight of the load, plus R3, reaction force sine theta 2 equals to R1, tension 1, sine theta 1. So this is the equation that we have built. Okay, so if you look at the question here, the question say the load is moved towards P. Okay, so the weight of the load over here will be moving towards P, therefore you get further away from the axis of rotation. Okay, that's the situation that we are being given. We are carrying this load to the left. So the new position of the load will be somewhere around here. Okay, so it's definitely before that you have a shorter distance. This is shorter distance R2. Then now your new distance is a greater distance R2. Okay, so what you know from here is that R2 will increase. The weight is still the same weight, constant. The distance from the axis of rotation to the reaction force is still constant. The reaction force, you don't know whether it will change or not. That's what they're asking for. The theta here also don't know whether it will change or not. Don't know whether the R is pointing in this direction or it will be pointing slightly at a greater angle or a smaller angle. You're not sure, so you leave it like this. R1 here is the distance from the axis of rotation to T1. That one is fixed. Your tension is always exerted at the far end. You always set this point as the axis of rotation. Therefore, the R is fixed. So this one is constant. You don't know how the tension will change. It might get greater, it might pull greater, or it might be weaker tension. You don't know, so leave it blank. But the sine theta over here, the theta here, you know the direction of the tension must be along the rope away from the object. So this theta here is fixed because you are not changing the angle of the string. You are not making the string more at a greater angle or a smaller angle. The string still remain in the same angle. So theta here should be the same angle. So this is constant. Okay, so the only thing that may change is the tension. The only thing that may change is the tension, is the reaction force, and the theta over here. Okay, so the situation that they tell you is that R2 increase. So if the left hand side of the equation experience increase, you know that the right hand side of the equation should also experience an increase. So therefore we know that tension 1 will increase. So tension will be increased, but they're asking for the quantity that will be decreased. Therefore we know that tension is not the answer. Okay, then the next thing is this, because we don't know whether R will increase or decrease, we don't know theta here will be increase or decrease. Let's just call this whole thing here as R sine theta. So you know that if we have something on the left hand side that increase, what should you do in order to make the equation equals is this part here should actually decrease. Okay, There's two ways of making the equation continue to balance. One is we make the right hand side increase. The second one is if this side increase by how much, then you decrease by something similar or something smaller. Or it can be this one. Let me use number to show what I'm trying to say. Let's say 5 plus 2 is equals to 7. If now you increase this to 8, there's two ways you make the equation balance. One is by you make this one to be equals to 10. You increase this one. First way is you increase this side, you keep this one constant. So this is one method. Second method is you keep this one constant, but you decrease this one. I'm not giving a good example. Should I pick such a big number? Let's say I pick 6. Okay, so what can I do is I decrease this one. So that's another option. So this is second option, or it can be a combination of both. So it can be, I put this as 7.5, means by it increase, but at the same time I also decrease this one, it becomes 1.5. So it can be a combination of both. This is the third method to look at the force. So let's say if so what will happen is the only thing that is possible to decrease here will be r sine theta 2. Okay, what will be decreasing here will be r sine theta 2. r sine theta 2 is the vertical component of the reaction force. Therefore, we know that it's the vertical component of the reaction force at point Q that will decrease. So this is the answer. Okay, the horizontal compressive force in the rod here, whether it will increase or decrease, well, if you look at the tension over here, you know the tension increase. So if the arrow here gets longer, the horizontal component should also increase. This tension, it becomes greater, then when you resolve it to the horizontal component should also get greater. So this will increase actually. Okay, so if you know this one increase, then you know r cos theta 2 should also increase because you want to balance it out. Okay, these two forces, horizontal component here, should be balanced. Okay, but whether the reaction force at Q, whether it will increase or decrease, right? You know that this r sine theta 2 here will decrease. You know that the vertical component will decrease. You know that the horizontal component will increase. So before that, if it's something like this, then now it becomes longer in the x direction, it becomes shorter in the y direction. So whether the r will be a different value or not, well, we are not sure. You have to use your Pythagoras, you have to plug in some number to check whether the reaction force remain constant or it increase or it decrease. Because it's not that both of them increase. If both x and y increase, then we know r will increase. If both x and y decrease, then we know it decrease. But now x increase, y decrease. So we don't know whether it's increase or decrease. So we can't be sure about it. Therefore, the reaction at Q, we are unsure. The only thing we are sure is that the vertical component of the reaction force at Q will decrease. Because if you increase the R over here, it's either increase the tension or you decrease the vertical component of the reaction force at Q. Or you do both, increase the tension and reduce the reaction force, vertical component of reaction force at point Q. Okay, so the answer is this one. So that's how you solve question 5. Let's move on to the next question. A ladder of weight W, which is resting on the rough floor. So this floor here on the ground here, it's rough and leaning against a rough wall. So this wall here, it's rough as well. Is at the point of slipping. The forces at the ends of the ladder against the wall. Okay, ends of the ladder, there are two ends of the ladder and there are forces acting on it. Forces acting on it, forces acting on the two ends of the ladder. Okay, so there are forces at the ends of the ladder against the wall and the floor are X and Y respectively. Or the forces at the ends of the ladder against the wall and the floor are X and Y respectively. So the force exerted by the floor is Y, the force exerted by the wall is X. Now they ask you to choose the figure that correctly shows the direction of these forces. Okay, so let's draw a free body diagram. Start by using a line to represent the ladder. So let's say this is my ladder. Then you know that if you ask ourselves the 5 question, the first question is, does the ladder has mass or not? Well, they immediately tell you that the ladder has weight. So you know there should be a weight pointing down from the center of the ladder. Okay, we assume it's a uniform rigid body. Therefore, the weight should be coming out from the center. Okay, next, is it attached to any strings, ropes, or cable? Well, it's a ladder. It's not connected to any strings, ropes, or cable, so there will be no tension. Next, is there any external force, or is there any force being explicitly mentioned in the question, or is there any force being explicitly mentioned in the diagram? Well, they mentioned forces acting by the ladder and the wall, but we will assume that as reaction force, or normal force, or frictional force later. Okay, so there is no external force. Next, is there any friction which is relevant? Well, they explicitly mentioned that it's a rough floor and it's a rough wall and it's at the point of slipping. So they are repeatedly emphasize that this is related to friction. So definitely there will be friction involved. So it says that it's a rough floor and a rough wall. So the friction should be at the wall and at the floor. So let's try to think about it. The ladder will be going to sleep. Okay, the ladder will be sleeping. If it's sleeping, then you slip down like this, right? This is how a ladder will sleep. So at the floor, the ladder will try to slip to the left, and friction is trying to prevent that from happening. So to prevent that from happening, your friction will have to point towards the right. Okay, your ladder you want to slip to the left, so the friction want to prevent that. So prevent that means that the friction should be pointing to the right. So this is the friction at the floor. Okay, next we know that the wall is also a rough wall as well. So you know that the ladder you want to slip like this, you want to slip down like this. Okay, so if you want to slip down like this, that means the rough wall here is preventing that from happening. If the rough wall is preventing that from happening, the frictional force exerted by the rough wall should be in the opposite direction to falling. So it should be pointing upwards. So this is the frictional force. This is the frictional force exerted by the rough wall. Okay, so I believe that's the only two places where you have your friction. Next, you move on to the last question. Is there any hinge or is there any pivot? Well, you can consider this place to be a hinge because it is in contact. You can think of it like a hinge. So this one you can also think of it like a hinge. But in this situation here, because you have already considered the friction, that means you don't need to consider everything regarding reaction force. Okay, reaction force, right, is a combination of friction and normal force. Okay, sometimes if it's a hinge, right, a hinge is a complicated structure, then there will be normal force pointing in very complicated direction, and there will be friction pointing in very complicated direction. So if we choose to neglect those complications, we can just combine the friction and the normal force and call it as reaction force. But now in this situation here, we have already correctly identified the frictional force. That means we don't have to look at everything about reaction force. We say reaction force is made of friction and normal force. We have determined the friction. That means now we determine only the normal force. That will be enough. Okay, the ladder is in this at this angle over here. That's our floor. Our floor, this is the horizontal surface. So the normal force should be perpendicular to the surface. And you know the floor should be pushing the ladder upwards to prevent it from falling. So therefore, the normal force should be pointing in this direction. So this is a normal force exerted by the floor on the ladder. Okay, then also you know that the ladder is like this, the wall is like this. So this is the surface. Your normal force should be perpendicular to the surface. Therefore, your normal force should be pointing to the left. Okay, your object here will be falling like this. So if you're falling like this, you'll be falling into the wall. You're preventing it from getting into the wall, so you must be pushing to the left to prevent it from falling into the wall. Okay, so this will be the normal force exerted by the wall on the ladder. Okay, so now if you look at the answer in here, they don't split their reaction force into normal force and frictional force. What they do is they combine everything and call it the force exerted by the ladder and the force exerted by the wall. So therefore we should combine the normal force and the frictional force. We should combine the normal force and the frictional force both at the floor and the wall. Okay, the floor and the wall, if you combine them together, the force that you will see will be pointing in this direction. So this will be the force exerted by the wall, or as we call it, it's a reaction force exerted by the wall. Okay, the normal force and the frictional force here, when you combine it, you are unsure whether you'll be pointing in this direction or you'll be pointing in this direction. But never mind, the question is not that complicated. Just pick one point, then you say it's the force exerted by the floor. Okay, it can be either above the ladder or below the ladder. Okay, but just by combining it back, you can see that the direction of the force will be following diagram C over here. So Y here will be representing the force exerted by the floor, X here will be representing the force exerted by the wall, and W here will be representing the weight of the ladder. This force exerted by the floor and the force exerted by the wall, we can call it as reaction force, because it's a combination of friction and normal force. Okay, so that's how we solve question 6. Let's move on to the next question. Question 7. The figure shows a heavy uniform plank of length L. So this is a plank of length L and is supported by forces F1 and F2 at position of L over 8 and L over 4 from the ends. So at L over 8 from the left end, you have force 1 pushing it upwards. At L over 4 from the right hand end, you got F2 supporting it. So now they ask for the ratio of F1 and F2. Okay, so this is a diagram being enlarged over here. So let's try to draw a free body diagram for the plank over here. So we are going to illustrate all the forces acting on the plank over here. So this black bar over here is representing the plank over here. It's just a straight line. Okay, don't think too much about it. It's just a thick straight line. Okay, so now you ask yourself the 5 question. The first question is, does this plank here has mass? Well, it says it's a heavy uniform plank. So heavy means by it definitely has mass, so definitely has weight. And it says it's a uniform plank, therefore you know that the weight of the plank should be coming out from the center of the plank. Okay, because it's a uniform rigid body. So here you get your weight of the plank. Next, is this plank over here connected to any rope, strings or cable? No, they didn't say anything here. There's no strings, no ropes, no cable in the diagram, so no tension. Next, the third question, is there any force being explicitly mentioned in the question? Well, there's F1 and F2. They say this F1 and F2 here is given support by something. So you can think of it as an external force. So let's label the external force here. So you know one of them will be closer to the end. Okay, when you draw your forces, always make sure that your arrow comes out from the object. Okay, the arrow must be coming out from the object, not pointing towards the object. So you need to shift your arrow so that it comes out from the object. So this one we call it F1. Then another one should be around here. This one we call it F2. Okay. Fourth question, is there any friction relevant to this situation over here? Where it's not in contact with any rough surface, so definitely no friction. Is there any reaction force, any hinge involved? Well, there's no hinge involved. They didn't mention anything fixed or any hinge or any pivot here, so no reaction force involved. So this is the diagram, the free body diagram for this plank over here. Now we are interested with the ratio between F1 and F2. Well, anything, you also start with the same idea. You know that this bar here, this plank here is not rotating, so you know that the sum of torque will be equals to 0. Okay, so you know that there are 3 forces over here. You are interested with the ratio between F1 and F2. That means you're interested with both of these. If you're interested with F1 and F2, that means you are not interested with the weight of the plank. Therefore, where should you pick as your axis of rotation? You should pick the point where you are not interested in. Okay, so now you pick your point. This point here is the point where you are not interested in. Now you can start to construct your equation. You are supposed to make a table, but because I don't have that kind of space and that kind of time to construct a full table, I'll just tell you that this force 1 over here will be creating a positive, a negative torque, because if you push in this direction, the pen will rotate clockwise. So this is a clockwise torque, so it's a negative torque. Okay, F2 over here, if you pin your axis of rotation here, then you push up at F2, you see that the pen here rotate anti-clockwise. So this is a positive torque. Then the distance from the axis of rotation, you know that this is L over 8. And you know that because this is from the center, and this is L over 2, right? Okay, so L over 2 minus L over 8, what you get is you get 3L over 8. Okay, you get it from taking L over 2, which is 4 over 8L, minus 1 over 8L, you get 3 over 8L. So this is the distance from the axis of rotation to the point where F1 is being exerted. So this is not relevant. So this will be negative 3L over 8. Then the force perpendicular will be F1 straight away. Okay, because you don't need to resolve this F1 over here. Next, you look at F2, the distance, the distance from the axis of rotation to F2 over here. What's the distance? You know that the whole distance here, it's L over 2. And you know that this distance here, it's L over 4. So L over 2 minus L over 4, you get L over 4. Okay, so with that said, you know what you should substitute for R will be L over 4, and the force perpendicular will be F2. So you know that this sum of torque here will be made up of a negative torque due to force 1 and a positive torque due to force 2. Then therefore you know that it will be negative 3L divided by 8 force 1 plus L over 4 force 2. Okay, so now we are trying to find a ratio between F1 and F2. That means later we want to construct an equation to be F1 divided by F2 equals to what? Then let's say if it's equals to A and B, then the ratio will be A dot B. Okay, so that's the idea. That's what we want to go for. So let's shift around our equation. We keep L over 4 times F2 on the left hand side. We bring things that are negative to the right hand side. So it will be 3L over 8 F1. Okay, so we want to build F1 divided by F2, right? So let's bring F1 divided by F2 over here. So L over 4 times 8 over 3L. So we cancel out the L, 4, 2. So you get F2 divided by 3, it's F1 divided by F2. Therefore, you know that the ratio between F1 to F2 will be equals to 2 to 3. So our answer will be this one. So you should expect that the force over here will be greater than the force over here. If you are further away, to create a equal amount of torque, to create an equal amount of torque, you need less force. If you are nearer to the axis of rotation, you need greater force to create that same amount of torque. You reduce R, you have to increase F. You increase R, you have to reduce F. That's why this one will be smaller than this one. That's why this one will have 2, this one will have 3. Okay, that's the idea behind question 7. Let's move on to the next question. A uniform rod is supported at point P and point Q. The support at P and Q are moved in a direction shown by forces of equal magnitude. So that means this support here is being pushed to the right, whereas this support here is being pushed to the left. And they ask which of the following is true. Okay, so we have our rod over here. It's a uniform rod. Then we have support on this side of the rod and this side of the rod. Then we push it with this force, and this force here are having the same magnitude. So they ask what they are asking for. They're asking that which one will slide first. Then why is it so? Why this one will slide first? Okay. So let's try to draw a free body diagram as usual. So we have a straight line here to represent this like uniform rod here. So this uniform rod here, if we ask ourselves the 5 questions, we will know that there will be a weight coming out from the center because this is a uniform rod. Next, you know that there will be normal force at these 2 points over here. This is the normal force exerted at point P. This is the normal force exerted at point Q. Okay. Of course, there will be friction. So when you're pushing it with force pointing to the right, there will be friction pointing to the left. So this is the friction. No, this is not. No, this is not here. This is the friction exerted on the friction exerted on the support over here. This is not the friction exerted on the plank. Okay. So if you push over here, there will be a resistance exerted on this support over here to the left. So technically, if you want to look at the friction experienced by the P over here, it should be pointing to the right. But let's not talk about friction. The friction is irrelevant over here. Okay, the friction experienced at P will be balanced out by the friction exerted experienced at Q. So we don't need to label the friction. The friction is relevant when you talk about this thing over here. This thing over here is experiencing a friction, and the friction is pointing to the left because it is this force here is here to overcome the friction that is pointing in the opposite direction. That's why the friction experienced by this support over here is pointing to the left. The friction experienced by this support will be pointing to the right because this force over here is trying to overcome the friction that is in the opposite direction. Okay. If you insist of labeling the friction experienced by P, right, then the friction will be opposite the direction of the friction experienced by the support. If the support experience a friction pointing to the left, then the plank will experience a friction pointing to the right. Okay, you can label it actually. Why is it in the opposite direction? Because of Newton's third law. If the plank exerts a force on the support will exert an equal magnitude opposite direction force on the plank. Therefore, this will be the friction experienced at point P. This will be the friction experienced at point Q. Okay, if you look at the support, this is support P, this is support Q. Okay, what you know is that there's an external force exerted on the support P while it is there to overcome the friction, the static friction experienced at point P. Okay, let's call it friction exerted by the rod. Okay, this one will be a force, and this one will be the frictional force exerted by the rod. Okay, we assume that nothing has slide over here, so the external force here is equal to the static friction of the rod. The external force here is equal to the static friction of the rod. We assume that it haven't slide. Okay, but they're asking for which one will slide first, so you can assume it to be at the limiting static friction. Assuming it to reach the limiting static friction, then you begin to slide. Okay, so which one will slide first? We know that this static friction of the rod, if you look at the limiting static friction max at point P, okay, it will be equals to mu s times the normal force experienced at point P. Okay, so it's relevant to this normal force at P over here. Whereas this frictional force exerted by the rod, the maximum frictional force exerted by the rod on support Q will be equals to mu s times the normal force at Q. Okay, technically what is this trying to say here is, if you think of this thing here having a ground, right, there should be a normal force exerted by the ground on support P. At the same time, this thing here has weight, so this is the weight of support P. At the same time, because the plank is pressing on the support here, therefore there is a normal force exerted by the plank exerted by the rod on P, and this end rod P here exerted by the rod on P will be equals to the end normal force exerted by P on the rod, and this is equals to NP. Okay, same thing over here. If there's a ground, then this is the normal force exerted by the ground on Q. Then you have your weight of the Q. Then of course the plank is pressing on the support, so there'll be a normal force exerted by the rod on Q. So this end rod Q here, based on Newton's third law, you know that is equals to the normal force exerted by Q on the rod. Normal force exerted by Q on the rod is just normal force Q over here. Okay, I'm getting a bit too far. You don't need to think that much actually. Okay, so what you need to know is, if normal force at P is greater than normal force at Q, then the maximum static friction at point P be greater than the maximum static friction at point Q. At which place you have a greater maximum static friction, that place will slide later, because you need more external force to overcome it. The one with the least amount of force, least amount of static friction, least amount of maximum static friction, that place will slide first. Okay, so we have to determine which one has a smaller magnitude of force for normal force over here. Okay, so the idea is again quite similar. You are not interested with the weight of the rod, so what you do is you take this point here as your axis of rotation. So if you take this point as your axis of rotation, you can see that the distance here, let's call it RQ, is very much greater than RP. Okay, so you know that the equation for torque is RF sine theta. And you know that for this situation here, everything here is 90 degrees. So you can remove this one. So you are left with RF. So torque 1 will be R1 F1. Torque 2 will be R2 F2. Well, I'm not considering a direction now. I'm talking about the magnitude now. Okay, so if you look here, R1 here will be, why do I call it 1? I can just call it P and Q. So torque P will be RP FP, torque Q will be RQ FQ. Okay, so torque at point P, RP FP. RP here is smaller than RQ. So if RP here is smaller, that means you have a greater force in order to balance it. If this one is greater, then this one will be smaller. You know that torque P must be equals to torque Q. Okay, torque P is equals to torque Q. So if one has greater R, it must have smaller f. If one has less f, it must have greater f. Okay, so you know that the force at P will be greater. That means NP here will be greater than NQ. So if you know NP is greater than NQ, then you know that the maximum static friction at P will be greater than the maximum static friction at Q. Okay, so if Q experience less static friction, that means Q will slide first, because it's easier to overcome the maximum static friction at point Q compared to point P. Therefore, sliding should occur first at Q. So this one is wrong, this one is wrong. Sliding first occur at Q. Now we see which one is correct. Then they say because the reaction force at P is greater than Q. Because the reaction force at Q is greater than P. Okay, so which one has a greater reaction force? The reaction force is combination of friction and normal force, right? So we know that MP will be greater. MP is greater than NQ. We also know that the friction at P will be greater than friction at Q. So both of these are greater than both of these. So at P, definitely the reaction force is greater. So the reaction force at P is greater than Q. This one is correct. Therefore, our answer will be this one over here. Sliding first occurs at Q because the reaction force at P, the reaction force at P, the reaction force at P, the reaction force at P is bigger than the reaction force at Q. The reaction force at Q, the reaction force at Q. Okay, so that's how you solve question 8 over here. Let's move on to the next question. So moment of inertia. Okay, and then it asks moment of inertia is more affected by the amount of mass than the distance that mass is from the axis of rotation. And they say the moment of inertia is a tendency of an object to keep rotating once set in motion. The moment of inertia is greatest for a solid sphere. Then moment of inertia is the tendency for an object to keep moving in a straight line once set in motion. Okay, we know that moment of inertia, it's the rotational version of mass. Okay, if you are in linear motion, you do everything using mass. If you are in rotational motion, then you do everything using moment of inertia. It's the rotational version of mass. So mass last time, the definition is the tendency. It's the okay, let me do it slightly slower. It's the quantitative measure of inertia. Okay, we see that mass is the quantitative measure of inertia, and inertia is the tendency for an object to keep moving in the straight line once set in motion. That's the meaning of inertia. Okay, so this is the definition for inertia. Okay, and because we are asking for moment of inertia, not inertia, therefore this is not the answer. Okay, next, we know that it's the rotational version of mass. So technically, it's the rotational version of the quantitative measure of inertia. So you have to change this statement here to a rotational version. So that means it's the tendency for an object to keep rotating once set in motion. So this is the rotational version. Rotational version, then you'll be like this. Therefore, this is the correct answer. So this is our answer over here. Okay, it's a rotational version of mass, means what? It's a rotational version of inertia. So rotational version of inertia means when you change this definition of inertia to the rotational version. So it's a tendency for an object to keep rotating once set in motion. Okay, so next, we look at the other two statements over here. Moment of inertia is more affected by the amount of mass than the distance that mass is from the axis of rotation. Well, this statement here is false because moment of inertia is equals to the sum of mi ri square. So if you have many particles, then you have to add particles one by one. So you know that over here, look at this equation, you know that r will affect more, okay, because a double of r will cause a quadruple increase of moment of inertia, whereas a double of mass will cause a double increase of moment of inertia. So which one affects more? Definitely the distance of the mass from the axis of rotation will affect more, because there's a square over here. So it's less affected by the mass, it's more affected by the distance of the mass from the axis of rotation. Okay, so this statement here is wrong. Next, moment of inertia is greatest for the solid sphere. Well, technically no. Okay, this one you should make comparison in order to say properly. But solid sphere usually has a lower moment of inertia actually, because you have quite a lot of mass near the center. Something like a ring will have a greater moment of inertia. Ring is like a donut shaped thing, so you have nothing near the center. So if your mass is not near the center, then your r will be very big, okay, because all the mass are far away from the axis of rotation. And if your ring is like this, nothing in the center, so most of your mass will have a great r. So if most of your mass has a great r, then you have a greater moment of inertia. That means that ring has a greater moment of inertia compared to a solid sphere. So solid sphere is definitely not the greatest, so that's wrong. So our answer is moment of inertia is the tendency for an object to keep rotating once set in motion. Okay, so that's it for this question. Let's move on to the next question. Question 12. A tire is fixed to an alloy rim and another identical tire is fixed to an iron rim. Okay, you have an alloy rim and you have an iron rim. So the two rims are of the same dimension. Okay, I'm not sure whether you know what is rim. So if it's a tire probably looks something like a circle. Then something like this, then you have your spoke, something like this, right? So what I am going to trace here will be representing the rim. So this is the rim. Okay, the steel part, this is the rim. Okay, so now they say that you have two rim, one is an alloy rim, one is an iron rim. The two rims have same dimension, and now both of the rim are rotated from rest. He found that it is relatively easier to rotate the wheel with the alloy rim. If you see it's easier to rotate, means by in a linear version is easier to push. Easier to push means less mass, right? So easier to rotate means smaller moment of inertia. Okay, so this statement here tells you that the alloy rim is easier to rotate. That means that the moment of inertia for the alloy rim will be less than the moment of inertia for the iron rim. Okay, so now you know that the moment of inertia for the alloy rim is less than the moment of inertia for the iron rim. Now you can move on to look at why is it so. Is it because the mass of the alloy rim is smaller? Or is it because the material is denser or mass is more uniformly distributed and the material is stronger? Okay, so what are the things that cause a change in the moment of inertia? We know that moment of inertia depends on both the mass and it depends on the distance of the mass from the axis of rotation, and the axis of rotation should be at the center. So this one is also affected by mass and the distance. Okay, so the material is stronger is not relevant, because what does it mean? Does it mean greater mass or smaller mass? No. Does it mean greater distance or smaller distance? No, it's not relevant. Okay, so therefore this fourth option is not the correct answer. Next, the mass of the alloy rim is more uniformly distributed. Well, this is not relevant to the question actually. They say the two rims have the same dimension. They should actually say both of them are uniformly distributed, because it is unfair to compare two rims that are not having the same kind of distribution. So you assume both of them to be having uniform distribution. Not a good question. Okay, you have to assume both have the uniform distribution. Okay, next, the mass of the alloy rim is smaller. If the mass of the alloy rim is smaller, then you decrease the m, then definitely it will cause a decrease in your I, right? So that is very much a possible option. So you put this one as a tick. If you decrease the mass, you decrease the moment of inertia, then you cause the moment of inertia to be less, thus easier to rotate. Everything makes sense. Next, if the material of the alloy rim is denser, if the material of the alloy rim is denser, you know that both of the rims should have the same shape, same dimension. So you should expect that both of them should have the same same volume. So if they have the same volume, then if alloy rim is denser, then that means alloy rim will have greater mass. Okay, greater density, same volume, then it means greater mass. So if alloy rim is denser, that means alloy rim has greater mass. Alloy rim have greater mass means alloy rim have greater moment of inertia. So that's not the case. We want a smaller moment of inertia for the alloy rim. That's why the answer is the mass of the alloy rim is smaller. So that's how we solve question 12. Question 14. So let's look at the question. Which axis gives the largest moment of inertia I for the disk? So you are given three options here. The first option is a disk, a circular disk with the axial rotation passing through the center of the disk. Second, you have the same disk, but now the axis of rotation is passing through one point on the circumference of the circular disk. The last option that you have is again a same circular disk, but now the axis of rotation pass through the axis of symmetry of the circular disk. Okay, so these are the three options. Then they ask which one gives the largest moment of inertia for the disk. So what I do here is I prepared three diagrams here, and these three diagrams here represent three circular disks, but now it is viewed from the top. So this is a top view of what I have here as our option. So the first diagram here is a circular disc view from up top, and you have your axis rotation, this black dot here passing through the center of the circular disc. And the second diagram here is again a circular disc, but now the axis rotation is represented by this black dot over here, which is passing through one point on the circumference of the circular disc. For the third diagram over here, again you have a circular disc, but now the axis of rotation is passing through the half of the, is splitting the circular disc into two semicircles. Okay, you can say it's a axis of rotation that pass through the axis of symmetry of the circular disc. So these are three different ways we can rotate a disc. Okay, so if you think of this as a circular disc, right, then the first option will be rotating like this. Okay, so the axis rotation is at the center. Then the second option will be a rotation like this. You'll be rotating with one point as the axis of rotation. Okay, whereas the third one will be, oh, I don't have this, so this one is a bit difficult to show, but it will be something like this. You rotate something like this. Okay, this is your circular disc, you will rotate like this. Okay, so different way of rotating it. It's the same disc but different way of rotating it. Now they ask which one gives the largest moment of inertia. So we know that moment of inertia, it can be represented by this formula over here. It's the sum of little mass and the distance of that little mass from the axis of rotation. Okay, so I here can be 1, 2, 3, 4, 5 until infinity. So for the first mass, what you do is you take the mass of the first particle times the distance of that particle from the axis rotation square. Then you move on to another particle, you get the mass of that particle times the distance of that another particle from the axis rotation square. So you do it for all the particles that are on the circular disc, then you add them all up, then you get your moment of inertia. So what I do now here as a rough representation of the idea is I have split my circular disc into a few parts over here. So I overlay a square grid on this circular disc here to show that I split my circular disc into various parts. So I can call this M1, I can call this M2, M3, M4, M5, M6, M7, M8, M9, M10, M11, yeah. You know the idea. So each box over here represent one mass, and each mass here has a certain distance from the axis of rotation. Okay, so if I split like this, you can see that for this situation here, we have one box that is very near the axis of rotation. So I say one box is very near. Okay, next you can see you have 1, 2, 3, 4, 5, 6, 7, 8 box, which is the second nearest. It's still considered near, but not as near as the first one. So you have 8, which is considered near. And now if you move on to the outer circle, then you have 1, 2, 3. We ignore these corners over here. We think this corner can be patched up over here. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 which are considered far. Okay, so if you are near, then the R will be smaller. If you are far, then your R will be larger. So this will be what you substitute in here for the R later. Okay, I'm just doing a rough idea. I'm not putting in any numbers. I'm just letting you see what do we mean by the mass is far away. What do you mean by the mass is near? Okay, so if we move on to the second example here, then we can see that these three box here, it's at a similar level to this box over here. Okay, it's not exactly on top of the axis of rotation, it's slightly away. So we can consider them near lah. Okay, so we have 3 boxes which is near. Okay, then for the next level, you see there are 1, 2, 3, 4, 5. We have 5 which is considered far. Okay, and now you have another 5 which is considered very far, and you have another 5 which is considered very, very far. Then you have another 3 which is considered very, very, very far. Okay, so just by this comparison here, you can see that for this setup over here, if the axis of rotation is at the center of the circular disc, you can see that there are more boxes that are near the axis of rotation. Whereas if you put your axis of rotation at one point of the circumference, you can see that many boxes are actually quite far away from the axis of rotation. So you can see that if your setup is like this, you have more masses that are far away from the axis of rotation. Far away from the axis of rotation with a square means that it will cause an increase of the moment of inertia. So just by comparing this one and this one here, we will know that this second setup here will have a greater I compared to the first setup over here, because there are more particles that has a greater R from the axis of rotation. Therefore, if you add them up, you definitely add up to a larger number. That's the idea. If your masses are far away from the axis of rotation, you cause an increase in the moment of inertia. Okay, so now if you compare the second setup with the third setup, then you can see that for this third setup, we have five boxes here, 1, 2, 3, 4, 5, which is considered this level, considered very near. So you have 5 which is considered very near. Then you have another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is considered second level, which is considered 10, considered near. Okay, then next if you move on further outside, then you see 1, 2, 3, 4, 5, 6. So these 6 are considered far. Okay, I'm just doing this roughly just to get an idea of the whole situation. So just by doing this comparison, we can see that if you compare the second setup with the third setup, you can see that there's only 6 that are far away. Whereas for here, we have 5 plus 5 plus 5 plus 3, which is more than far already. So over here, definitely more boxes here are far away from the axis rotation. So if you compare this circular disc with this circular disc, this second setup here will still produce the greatest moment of inertia. Okay, because there are more particles that are far away from the axis of rotation. So our answer for this question here will be this one. This setup here will give us the maximum or the greatest moment of inertia, because most of the particles are at a distance, at a greater distance away from the axis of rotation. And now if you compare between this first setup and the third setup, you can see that you have more boxes which are very near. This is 1 boxes very near, this is 5 boxes very near. You have 8 boxes considered near, but here you have 10 boxes considered near. So this setup here has more particles that are near the axis of rotation. If this setup here has more particles near the axis of rotation, this particle here will have, this setup here will have less moment of inertia. Okay, so you should expect this one to have a least moment of inertia. Then this one is considered moderate moment of inertia. Okay, so that's a rough idea of how to determine which setup here will have greater moment of inertia, which setup will have less moment of inertia. Again, you have to make one assumption when you are doing this problem. You have to assume that all 3 setup here has the identical disk. Have identical circular disk. Means by the 3 disks that you see here should have the same mass. That's why when you cut it into equal boxes here, each boxes should have the same mass, no matter you are in the first setup, the second setup, or the third setup. Each boxes here should have the same mass. Then now you can directly compare it like that. If the first disk is more massive than the second disk, then you mess up our comparison already. We have to assume all 3 disks here have the same mass, all 3 disks here have the same size, all 3 disks here have the same thickness, everything the same, only you are able to compare it like this. Okay, so this is how we solve question 14. Let's move on to the next question. What would happen to the rotation of the Earth if the ice caps at the North Pole and the South Pole melts and the water produced flows toward the equator? Okay, so if I like to draw it out, then let's say you have this is your Earth. Then for your Earth, your ice cap is usually around here. Then another ice, this is Antarctica. Antarctica, the ice is usually around here. Then you know this is where your axis of rotation is for your Earth. So your Earth will be spinning around this axis of rotation with a period of equals to 24 hours. Okay, now if the ice cap melts, then that means that these masses over here will be going towards the equator. Okay, so previously it was at the pole, but now it has progressed towards the equator. So if I use blue to represent the after situation, then now the ice cap has melted into water, then that mass has been transferred to the equator. Okay, if now my mass is transferred to the equator, now if I view the whole situation from top, initially, and now this is a top view, this is top view. Initially the axis, okay, this is the axis rotation. Initially the mass are concentrated at the Arctic and the Antarctica. Let's say Antarctica is behind here. So this is where the mass of the ice caps is concentrated. Now, once it melts, it will go towards the equator. So equator is definitely far away from the axis of rotation. So it will melt and it will go towards the equator. Therefore, the water, the melted ice cap, will now be around this area over here. Okay, so the red is before, the blue is after. So now the process of the melting of the ice cap brings the masses from somewhere near the axis of rotation to somewhere far from the axis of rotation. Okay, we know that the equation for moment of inertia is sum of miri squared. So if the masses over here experience an increase, in the distance from the axis rotation, that means the moment of inertia should be increasing. Okay, the melting of the ice cap causes the moment of inertia of the earth to increase, because previously your r is small, the distance of the mass from the axis rotation is small, but after the ice cap has melted, the distance of the same mass from the axis rotation has increased. Okay, melted ice cap and the ice cap before it melts both have the same mass. They are the same quantity of matter, just that it was in solid state and transferred to liquid state. It's the same amount of mass, just that you redistribute it to somewhere far away from the center or the axis of rotation. Okay, so we know from here that the process here causes an increase of moment of inertia. So if we know that already, straight away we can cross out some of the answer here. I believe you can know that the moment of inertia of the earth decreases is wrong. In fact, it should increase. Okay. Next, they ask about the speed of rotation. So we have to do something about it. Rotational kinetic energy, it's out of syllabus, but the equation is half I omega squared. It actually comes from half mv squared, but rotational version of mass is moment of inertia. Rotational version of velocity is angular velocity. So this is the rotational kinetic energy. So you know your moment of inertia increases. So what about the omega? Okay, the speed of the rotation is omega, the speed of the rotation is omega. So we have to determine that. Okay, so to determine whether the omega increase or decrease or not, you have to apply the idea of principle of conservation of angular momentum. So know that the initial angular momentum will be equal to the final angular momentum. Okay, because in this situation here, there is no external torque. You don't have a Hercules standing here to go spin the globe or what. No, there's no external torque. It's just the earth rotating. There's no one go to exert a torque onto the earth. So in this case, the angular momentum will be conserved. So now once we know that already, we know that initial will be considered as I initial, moment of inertia initial, angular velocity initial equals to moment of inertia final, angular velocity final. So this is the situation right now. We change the angular momentum to be re-expressed in terms of moment of inertia and angular velocity. Now we know that initially the situation, we call it I initial and I initial, omega initial. But for the final situation, we know that the moment of inertia increases. Therefore, we know that I final will be greater than I initial because the moment of inertia increases. So if the moment of inertia increases, but this equal sign still remain equals, that means that our omega final must decrease. So if previously is 5 times 2, if previously is 5 times 2, now you change it to 10, then this one you have to change to 1, right? You have to bring it down. Okay, you want to make this equal signs continue to equal. So if this first term in this first parameter increase, then the second parameter should decrease. Therefore, the omega final should be less than the initial omega. Therefore, you know that the speed of the rotation should decrease. So this is the answer. Increases is wrong, it should be decrease. Okay, so now you know that already. You know that I will increase, omega will decrease. But because omega there's a square inside, right? The effect of the omega will be more severe. The effect of the omega will be more severe because there's a square inside here. Therefore, you know here it should be decreases. So our answer will be the speed of rotation of the earth about its axis decreases. So that means the spin of the earth will slow down because of the ice caps melting. Okay, so this is how we solve question 16. Let's move on to the next question. A toy train travels along a track fixed to the rim of a wheel whose axis of rotation is vertical. Okay, so we have a track. That track is fixed to the rim of a wheel. So this is a wheel. Then this part here, This is the wheel. This part here will represent where the rim is. The rim is the circumference of the rim. Okay, so you have a track fixed along this red line here, which is the rim of the wheel, and this rim here has an axis of rotation which is vertical. So our axis of rotation is somewhere at the middle and it's pointing outwards towards you. So that's the axis of rotation. This is the wheel, and the axis of rotation is pointing outwards towards you, so the wheel will rotate like this. Okay, of course, if you flip it up, then you consider the axis of rotation to be vertical. If you install the tire to be flat, then the axis of rotation will be vertical. Okay, so now the mass of the wheel is greater than the mass of the toy train. So the mass of the wheel is greater than the mass of the toy train. Okay, so initially both the train and the wheel are at rest and there is no external force. So previously there's omega should be equal to 0 because the wheel is at rest. Then the train is not moving, so the speed of the train should also be equal to 0. And there is no external torque, therefore you know there's no external force. That means there is no external torque. That means your angular momentum will be conserved. Okay, now when the train starts to travel around the track, the wheel will rotate like how? Okay, so this situation here, you have a track, then that track is attached to the wheel, and you have a square here to represent the toy train. Now initially all of them are at rest, so if you know that the angular momentum is conserved, so let's write it down. The initial angular momentum will be equal to the final angular momentum. Now you know that initially everything is not moving. Okay, we have two objects here, so let's sum it up. So initially everything is not moving, so the initial angular momentum should be 0. Okay, because the v here equals to 0, so the angular momentum of the toy train will be equal to 0. The omega here is 0, so the angular momentum of the tire here will be 0 as well. So the initial angular momentum is 0. But how about final? Final, what happened is the train is moving. Okay, so the train is moving, the v is no longer equal to 0. Therefore, you have an angular momentum for the toy train. Okay, but you know that initially is 0. That means if the toy train has an angular momentum, then the wheel will have also another angular momentum, and these two angular momentum should cancel out so that the final angular momentum remains at 0. Then only your angular momentum can be conserved. So let's try to find how to do that. We know that this toy train here is moving in a circular path, and this toy train here has a mass of m. So we can use the formula of, okay, so the L, the angular momentum for the toy train, can be equals to mRv. Okay, so this is the equation for you to determine the angular momentum for a particle. So this one, we call it the mass of the toy train, the radius of the toy train, and this one will be the speed of the toy train. So this one will be, let's write it down slowly. This will be the angular momentum final of the toy train plus the angular momentum final of the wheel. So there are two components here. One of them is m, the mass of the train, plus the distance of the train from the axis of rotation and the speed of the train. Next thing, we know that this wheel can be rotating as well. So this wheel, it's a disc shape kind of thing. So it's a uniform rigid body and with the axis rotation at the middle. So for this one, we will use the formula of I of the wheel, the moment of inertia of the wheel times the omega of the wheel final, omega final. Okay, so this is the equation to represent the angular momentum final for the wheel. Okay, I omega is used when it's a rigid body where you know the moment of inertia. MRV, RMV, depends on how you arrange it. This one is for a particle that is traveling at a certain distance away from the axis of rotation. Okay, this is a particle. This is a uniform rigid body. Okay, so now we know that the mass, the distance is constant. You're not making the circle larger. You're not changing the toy train to become more massive. This is constant. And you know that the moment of inertia of the wheel should also be constant. Okay, you are not making the wheel larger, you are not making the wheel smaller, you are not doing any changes to the wheel. You are only making it possible to rotate. That's all. Okay, so if you make the toy train move, that means you increase the speed of the toy train, making it from at rest 0 to a non-zero value, moving. So if you increase the speed over here, what will happen is if you want to keep the left hand side at 0, then you have to introduce something negative over here, right? So because this whole term here is positive, then you have to plus with something negative, only you can become 0. So if initially this one, if initial angular velocity is 0, that means this one you have to go down. You have to enter a negative value. That means it is spinning in the opposite direction in order for you to cancel the angular momentum of the toy train over here. Okay, so this one you take it as positive. So this whole term here will be positive. Then you plus together with this whole term here, which is negative. Then positive plus negative, only it's possible to be 0. So that means this angular velocity here, the angular velocity of the wheel here, will be in the opposite direction to the motion of the toy train. So this is the conclusion that we can make. So if you see the wheel will rotate in the same direction, then you know it's wrong. If it's the same direction, then the omega here should be positive, the v here should be positive, both in the same direction. But no, the v is in positive direction, the omega is in negative direction, so opposite direction. So if you see anything with the same direction, then it's wrong. Opposite direction is correct. But whether it's the same angular speed or not, well, this one you have to determine. So the v over here, the speed of the train here can be equals to r, the distance from the axis rotation, times the omega of the train. Okay, then you can compare this omega of the train, compare it with the omega of the wheel. But they mentioned that the mass of the wheel is greater than the mass of the toy train. That means the wheel will not be able to rotate so easily because it has a greater moment of inertia. The moment of inertia for the wheel will be much greater than the moment of inertia for the train. Therefore, the angular velocity for the wheel will be much smaller than the angular velocity of the toy train. Okay, you can plug in your value to make sense of it. Okay, but I'm not going to do that. You get the video really long. The idea is this thing here has a large value, okay, because the mass of the wheel is much greater. So therefore, this moment of inertia has a large value. So if your moment of inertia here has a large value, then a big change over here will only cause a small change over here. Okay, you only need to change this by a little. So therefore, you should expect this one to only rotate with a very small angular velocity compared to the angular velocity over here. Okay, so the toy train will be moving much, will be finishing one circle with shorter time, whereas the wheel will be rotating slowly, so it take more time to finish one complete circular rotation. Okay, so it will definitely be a smaller angular speed. Same will be wrong. Okay, same angular momentum will be correct, just that in the opposite direction. But if you talk about speed, the wheel will be rotating slower, so it's a smaller angular speed. Okay, so that's how you solve question 17. Next question. An ice skater spins with her arms folded. So arms folded is something like this maybe. So when she extends her arm outwards, the angular momentum will increase, decrease, or remain the same. Okay, so this is actually, I think it's a trick question. If you read carefully, then I believe you will make the mistake. Okay, they're asking for what happened to the angular momentum. Well, for this situation here, there's no one go and touch the ice skater, go and spin the ice skater, so there is no external torque. So when there's no external torque, then the angular momentum will be conserved. Just by seeing this sentence here, you can say that the angular momentum should remain the same. Okay, many of you might be saying decreases. If you are saying decreases, what decreases is the angular velocity. Angular velocity decreases, but the angular momentum remains the same. The idea is like this. The initial angular momentum is like this, whereas the final is what? Okay, so if you look at this situation here, they extend the arm. So if you extend the arm, that means you bring the mass that is near to your body, you bring it far away from your body. If you're bringing it far away from your body, that means the R increases, then you are increasing the moment of inertia. So what happened here is you increase your moment of inertia. And if you increase your moment of inertia, what will happen is your angular velocity should decrease in order to keep both sides equal. So to give an example, if this is 5 times 5, 5 times 2, let's say. Okay, now if you increase your moment of inertia, then it will become 10, let's say. So what needs to happen for your angular velocity is it has to decrease. That's why it will spin slower when you extend your arm. Okay, so this is the video to demonstrate the situation. So in this situation, you see the person's hand, he will fold up her arm. She will fold up her arm, then observe what happened to the rotation. Then she will extend her arm. Then you see what happened to the rotation. So when he unfold her arm, then it's slow. But when she fold up her arm, you can see that it spins faster. Then when she unfold back her arm, then the spin becomes slower. Okay, so this is aligned with what we mentioned over here. When you unfold your arm, when you extend your arm, what you're doing is you're increasing your moment of inertia, causing the angular velocity to go down, so rotate slower. When you fold back your arm, what you're doing is you're bringing the masses near to the axis of rotation, which pass through your body from the top. Okay, this is your axis of rotation. Now you bring your mass nearer to the axis of rotation, then the moment of inertia will go down. So if the moment of inertia go down, let's say if the moment of inertia is small, then what will happen is the angular velocity will have to increase. Therefore, you can see the skater to be spinning faster. Again, this is the video. Extend slower, fold your arm faster. Then extend back your arm, come slower. Okay, so this is conservation of angular momentum being demonstrated in an ice skating example. Okay, so this is question 18. Let's move on to the next question. Question 20, the last question of this quiz. If the planet Jupiter underwent gravitational collapse, its rate of rotation about its axis would... Okay, so gravitational collapse is it's an astronomical phenomena in which the planet becomes smaller. Okay, you can think of it as collapse inwards towards itself. Okay, so for this situation here, if you like to draw it, then this is the initial situation of Jupiter. Then you can imagine it to be something like this. Then through the process of gravitational collapse, what happened is the size of Jupiter will become smaller. Okay, so if you imagine this is the axis of rotation of the Jupiter, and now it has shrunk towards something like this, then you know that the mass is now nearer to the axis of rotation. Okay, previously the masses are so far out from the axis of rotation. R is big, but now the mass is not so far away from the axis rotation. So R is small. So if your R is small, that means you're bringing the mass nearer. You can think of it as the ice skater folding up her hand. So when the ice skater folds up her hand, what does it mean is that the moment of inertia should decreases. Okay, so come back to the same idea. The angular momentum should be conserved. So if initially it's like this, then if you decrease your moment of inertia, then your angular velocity will have to increase. Okay, this is just a graphical idea. You don't write this in your exam. Okay, you decrease your moment of inertia, the angular velocity will increase. Angular velocity increase, that means it will rotate faster. So the rate of rotation should increases. Okay, so the idea is to apply the principle of conservation of angular momentum. So yeah, so when things get smaller, then you spin faster. Okay, so that's how you solve question 20, and that's it for quiz chapter 8 set 1. Okay, so thank you very much.